Hi guys, for today's lesson we're going to be dealing with instantaneous rate of change. So some rules to remember when calculating the rate of change of two variables, i.e. the rate of change is another word for pretty much saying the gradient. We have typically found the average rate of change. So this is like going back to year 8 mathematics when you're finding like simplified rates. That was always to do with some sort of average rate of change. So say if a car travels 500 kilometers over 5 hours, the average rate of change here between these two variables, distance and time, is going to be your 500 divided by 5, which gets you 100 kilometers per hour. There is your rate of change, 100 kilometers per hour. That would be like your gradient if you graphed distance over time on a number plane. So this is going to be your average speed in this situation. Note the instantaneous rate of change, i.e. in this case specific speeds at specific times for this journey cannot be calculated in this manner. We don't know like how fast they were going at a particular point in that journey. All we know is that on average they were going about 100 kilometers per hour. So to calculate the instantaneous at an instant rate of change of two variables, the derivative must be used. So the derivative allows you to figure out specific rates of change at specific times, not just find an overall average. So let's do some example questions on this sort of stuff. So a cockroach plague has hit the town of Orange. Precautions have been put in place to control the outbreak. The cockroach population in millions is modelled by the equation P equals 7 plus 16 minus T squared after T days. So pretty much this equation is telling you if you put in a value for T, which is just describing the number of days, it'll tell you roughly what the population is. So we know this model, this is helping us with our understanding of how the population is changing over time. But we want to know specific things about this population, like how do we use this equation to give us more information about this cockroach population. Okay, so first up, what is the population after 5 days? That's as simple as just putting in 5 into this value for T, and that'll spit out the population. So this equation is very handy. So if we let T equal 5, we get this equation here, which equals 12. So therefore, the population is 12 million after 5 days. Each one of these numbers of P, because it's in millions, it's going to be, so if this is 12, it means 12 million. Don't get confused, that's not meaning 12 cockroaches, it's meaning 12 million cockroaches. Okay, what is the population rate of change after these 5 days? So this 12 is a set number of cockroaches, but how is the cockroach population changing at that amount of time of 5 days? So to figure out a rate of change at a specific moment in time, we have to take the derivative of our equation. So to find the derivative of this P in terms of these T's here, so dP dt. The derivative of 7 is 0, the derivative of 6t is 6, and the derivative of minus t squared is going to be minus 2t. And we want to figure out what this is equal to after 5 days, so our t becomes a 5, and that is equal to negative 4. Now that negative 4 represents negative 4 million, and that represents a rate of change. So the population is decreasing, because it's negative, by 4 million, because it's 4, per day at day 5. We know that it's per day, because that's pretty much what these rates are talking about. Like they're doing it like it's to do with time. It's per, like the derivative of P in terms of time each day, which is measured in days. So this is the sort of conclusion that I need you guys to understand. What was the rate of change after just 1 day? So we've got our derivative, that's talking about rate of change, and instead of 5 days, we just want 1 day. So if we put in our value of 1 into our derivative of 6 minus 2t, which is number 4, we get that our derivative is positive 4 this time. So up here, the population was going down by 4 million. It was getting weaker and weaker, like the precautions were taking over and minimizing the population. But after day 1, the population was going up by 4 million. The population is increasing by 4 million per day at day 1. So this is where they did not have the population under control. It was getting worse and worse. So you can see after 5 days it was getting a lot better, but at the day 1 it's significantly getting worse. So like that's the idea behind this sort of situation. Like there's times where the population is increasing, and there's times where the population is decreasing. Okay, question D. When did the precautions cause the cockroach population to stop increasing? So we could see here that it was increasing, and here it's decreasing. When was that change? So the idea is we want our rate of change to be 0. When there's a 0 rate of change means that the population isn't increasing anymore. So when we see that our derivative is equal to 0, that means that the population is not going up anymore. It's stopped going up, and then it's going to start to go down. So the idea is we want to know when our derivative is equal to 0. So we rewrite our equation for our derivative. Let this side equal 0 because that's what we want, and we figure out what t is equal to. So we solve for t, which is 3. So at the day 3 mark, the population is no longer going up anymore. So after 3 days, the population stopped increasing. Make sure you've always got some sort of conclusion. When was the population fully eliminated? Well, we're concerned with like numbers for the population. So we're not considering rate of change here. We just want to go back to our original equation, which gives us numbers for the population. So we want our population to be 0. So we're going to change this side to a 0, and then we're going to solve. So we've got over here a quadratic. So we need to factorize this because we've got 2 t's that we can't get by itself. So when factorizing this, we want to get our t, well, our coefficient, our pronumeral, we want that to, the one that's being squared, we want that to be positive 1. We want it to be monic. So we can multiply this, well, both sides of the equation by -1. So our 7 becomes -7. Our positive 6t equals -6t, and our negative t squared becomes positive t squared. This is a lot easier to factorize. What 2 numbers multiply to give -7 and add to give -6? And the answer is -7 and +1. And then using the null factor theorem, we let each of these brackets equal 0, and then we can solve for t. So we get that t is equal to 7 and t is equal to -1. Because t represents time, you can't have -1 as a time, so you don't consider this part of the solution. So you only consider this side, which is positive. So therefore, our population is going to be 0 after 7 days, which is our final conclusion there. So after 7 days, the population was extinct. So after day 1, it was getting a lot worse. At day 3, it's starting to get better. And then after 7 days, it's completely gone. What is the average rate of change of the cockroach population over these 7 days? So because we're dealing with an average rate of change, we're just looking at the overall change over the whole period of time. So we could see that the population's completely gone after 7 days. So therefore, we pretty much define the average rate of change. We want to look at the start and the finish and see how long that took to go from start to finish. So find the difference between the starting and finishing populations, then divide by the number of days. That's the idea. That's the average rate of change per day. So the starting population, well, we can find that out by substituting in 0 for our t, which is describing the number of days. So when we do this, our starting population is 7 million, because it's 7 plus all these zeros. And the ending population is 0. So it's gone from 7 million at the start to 0 after 7 days. So that means the average rate of change, well, if we do the finished population 0 minus the starting population of 7 and then divide by the number of days, we get -1. That means that the average rate of change in the population was -1 million per day. And that makes sense because you started with 7 million and you ended with nothing over 7 days. So it's just slowly gone down by 1 million every single day to get to 0. We know that that actually wasn't the case. That's not what was happening. At the start, the population was actually going up. But on average, the population was overall going down because it eventually got down to 0. Hope this helps with the questions. Good luck.